All right. Well, it's a pleasure to host Hart Goldman from MIT today for our theory seminar. So Hart got his PhD from Urbana-Champaign, where he worked with Eduardo Fratkin, and well, he's done a lot of interesting work, and you're going to hear about some of it today. So Hart, go ahead.
Thank you for the introduction. Thanks for having me. I fondly remember the last time I was at Cornell several years ago visiting for grad school, and hopefully when this whole pandemic thing blows over, I'll be able to visit again. But in any case, today I'm going to be talking about some new work that I did with Sentinel on new microscopic construction for a family of bosonic fractional quantum Hall states. So the main setting for this talk is going to be something that many of us are already fairly intimately familiar with, namely the quantum Hall effect. Just take a 2D system of electrons in a magnetic field pointed perpendicular to the sample. And as we all know, the electrons in the absence of interactions are going to form highly degenerate Landau levels. And as you fill each Landau level, you will get a quantized Hall resistivity and vanishing longitudinal resistivity in what's known as the integer Hall effect. And really amazingly, when you turn on Coulomb interactions, you now can get new incompressible gapped phases when these Landau levels have fractional filling, as you can see in this plot, what's known as the fractional Hall effect. And understanding the fractional Hall effect and all of the various beautiful and wonderful physics associated with it was really one of the major triumphs of condensed matter physics in the past several decades. So in particular, speaking of that amazing understanding, these states are paradigmatic examples of topological orders, which have been fascinating for many of us over the course of our careers. And we know pretty much not everything there is to know, and I'll talk about some of the things that we don't know, but we know certainly the universal properties very well. So we have ground state wave functions. We know the universal response coefficients like the Hall conductivity and thermal Hall effect. And we know the excitation spectrum being anionic in fractional states. So if I create an excitation in a fractional quantum Hall state and I braid it around another one, rather than the wave function picking up a fermionic or bosonic phase, you get some intermediate phase theta, which is a demonstration of the fractional charge in statistics that is the hallmark of a topologically ordered state. And all of this is incorporated in a Chern-Simons low energy effective theory, which I'll define in a second. But in addition to all of this, we even know some things about dynamics. So we can use exact diagonalization to compute things like gaps. We can access the physics of collective modes, like the famous Griffin-McDonald-Platzman mode, ask questions about instabilities to things like stripe phases and many other types of interesting phenomena, although that's not within the realm of this Chern-Simons effective theory. However, we don't have any analytic framework capturing both the universal stuff and the dynamical stuff simultaneously. Dynamical here being a euphemism for non-universal. So the main question that I'm going to be asking in this talk is how can we try to bridge that gap? How can we go from a microscopic theory of electrons or bosons in a Landau level and get, at the end of the day, a Chern-Simons effective theory and be able to pretty much compute anything that we want, both universal and dynamical stuff. And we're going to ultimately answer this question for the specific examples of the bosonic Jain states. Okay, so a little bit more information on how we understand as theorists the fractional Hall effect. So much of this understanding is anchored on the notion of flux attachment and composite particles. So if I take my original system of electrons in a magnetic field and I adiabatically attach some flux quanta to each electron, so in this picture I have two flux quanta being attached to each charge, then you get a equivalent theory of what we call composite particles, where the statistics is shifted by pi for each flux attached, coupled to an emergent Chern-Simons gauge field, which implements this flux attachment. And in now what's a screened magnetic field, because as I attach each flux, I kill some of the background magnetic field. So I have now a new equivalent quantum Hall system, but now with this strong coupling to a gauge field. And I should also mention that this screening that happens, of course, is proportional to the density of charges, because I'm just attaching individual flux quanta to each electron. Okay. Also, anyone can feel free to interrupt me at any time throughout this talk. I think I forgot to say that. But yeah, and I also, I think I already said this, but each time I attach a flux, I shift the statistics by pi. So if the original particles are fermions, attaching an even number of fluxes will give me back composite fermions. And if the original particles are bosons, which is the case we'll focus on in this talk, you'll get composite fermions for an odd number of flux quanta attached. And amazingly, we can use this equivalence with composite fermion theory to explain the observed sequences of abelian fractional quantum Hall states, known as the Jain sequences. So you basically take these composite fermions, and now you have them fill their own Landau levels and form integer quantum Hall states themselves. And it turns out that the fillings at which these guys form their own incompressible integer Hall states correspond to this special sequence of filling fractions of the original charges. Here, P corresponds to the composite fermion filling, the number of Landau levels, and M is this number of fluxes that I've attached. And in particular, now that I have these gapped states of composite fermions, I can imagine integrating them out. And indeed, the low energy effective theory that you get is a Chern-Simons topological quantum field theory, which looks something like this ADA here, except a little bit more formally, you want to have a quantized coefficient in the numerator here. This is sort of, if you want schematic notation for how all that works. Okay, so now another interesting feature is that as the composite fermion filling goes to infinity, the magnetic field that they feel is going to 0. This should be B star, not B effective. And you get, as a result of that, now fermions feeling no external magnetic field. And so they're going to want to form a Fermi surface. And now this filling 1 over m, just taking P to infinity. And this is a famous composite Fermi liquid state. It's been something that I've studied quite a lot and it's kept many of us up at night. Very little is, well, we know a lot, but we also don't know a lot about this state. But one thing we can say about it is that we can view it as a parent to the Jain sequence. Namely, if I take this Fermi surface and turn on a magnetic field, dope it, that filling, again, these Landau levels of composite fermions gives us the Jain sequence. Okay, so the ordinary composite fermion approach has been really wildly successful in capturing universal properties, as I already alluded, since we get the right Chern-Simons effective theory. But ultimately, it is just an effective field theory, and this composite fermion construction is totally insensitive to physics at short length scales of order the magnetic length. In addition, the flux attachment transformation at the level of the wave function heavily mixes Landau levels. So if you want to talk about physics restricted to a single band, you're out of luck. In addition, there's generally quantitative failure with dynamical information, as you might have guessed, since it's just an effective theory. So it gets gaps wrong. You can't get things like the static structure factor and finite wave vector response, and so on. Although I should note that there's a Hamiltonian theory of the fractional Hall effect, which has a similar motivation to composite fermions, but it actually has the opposite problem where you can get some non-universal stuff, but you encounter challenges with the universal information. So can we do better? Now, before I explain how we're going to do better, I want to give a sort of philosophical interlude on why all of this matters. So one objection that I hear a lot when talking about this work is that it sort of defeats the purpose of doing effective field theory if you want some fully microscopic description of everything, and that non-universal stuff is often uninteresting. However, the answer to this is sort of twofold. The first is that tractable, strongly correlated theories that can interpolate fully between the UV and IR are extremely rare in condensed matter physics. And quantum Hall, just by virtue of how much we understand about it, is really one of the few reasonable problems where such a thing might be achievable. And the second reason is that quantum Hall is actually quite special. So if you take the limit where you have Galilean invariance and you project into a single Landau level, you get this enlarged symmetry structure, which for experts is known as the W infinity algebra. This isn't going to play an important role for us. I'm just throwing it up here. But as a result of this, the short and long wavelength physics ends up mixing. We'll see how this works in a minute. So really, even if we want to write down an effective theory for low energies, in this language, we should be talking about all wave vectors if we want to capture the lowest Landau level. Now, in one corollary of all of this is that a lot of things that we would otherwise expect to be non-universal actually get knowledge of universal data. So this is why the Hall viscosity knows about something called the shift of quantum Hall states on the sphere, which is a universal topological thing. Similarly, the static structure factor is, which is the Q to the fourth term in the density correlator, is bounded by this thing called the shift. The dynamics of the collective modes also know about this. So we would really like a theory that respects all of this physics. Okay, so how are we going to do that? Well, we're going to use a effective theory that was constructed for the composite Fermi liquid state of bosons at nu equals 1. So if you remember from a few slides ago, this corresponds to a single flux attached to the fundamental bosons in this problem. And what Jihuan Dong and Senthil found is that you can write down a non-commutative composite Fermi liquid effective theory that lives on this, that lives projected onto a single Landau level where space becomes non-commutative, and we'll see why in a second. And this theory is nice because it's low energy. It lives below the interaction scale of the parent Hamiltonian, but it captures physics at length scales shorter than the magnetic length. So it's like a low energy, all wavelength description. And what we're going to do is take this theory and extend it to the Jain states. So we're going to dope this composite Fermi liquid theory with a magnetic field, and it's going to fill some non-commutative generalizations of Landau levels and give us the Jain sequence states. And immediately we're going to get new approximate expressions for the Jain gaps out of this. And we'll also be able to show that the low energy effective theory is a non-commutative Chern-Simons theory, which is something that people in the quantum Hall world have batted around for 20 years, but to my knowledge, this is really the first microscopic justification for such a theory. Okay, so it's a general roadmap. First, I'm going to talk about how you can get the bosonic Jain sequence from a cartoon picture of single particle physics of composite fermions built out of charges and dipoles in the lowest Landau level. If you take anything away from this talk, it should just be this simple physical picture. You can really get all of the physics out of it. Then I'm going to explain how this all is equivalent to this exotic non-commutative composite fermion field theory. And finally, if I have time, I'll talk about how to integrate out the composite fermions and get non-commutative Chern-Simons theory. Okay, so now I'm going to talk about this dipole quantum mechanics picture. So we want a composite fermion framework directly in the lowest Landau level. So just as a reminder, when we project to the lowest Landau level, the gap between the lowest Landau level and the first Landau level is just set by the cyclotron frequency. So taking that to infinity is what takes us to a single Landau level. And therefore, the only thing going on between particles in this now flat band, there's no dispersion, is just the interactions between them. So what this means is that the kinetic energy gets quenched, and the Hamiltonian is just the density-density interaction written here. So this could be Coulomb. For our case, we're going to be thinking about a contact interaction, which is a bit more relevant to trying to realize bosonic quantum Hall states in cold atoms. But you can pick any potential you want here. Okay, so one consequence of this projection is that space becomes non-commutative. To see why, you just think semi-classically, each particle in the Landau level is going to be undergoing some cyclotron orbit and can be described by two coordinates. One is a guiding center coordinate, and the other is what we call the orbital coordinate, which is essentially the momentum. And when we project into a Landau level, because we're killing the kinetic energy, we kill off this coordinate here. Essentially, the quantum mechanics problem describes transitions between Landau levels. And so we're just left with the guiding center defined here. But the guiding center coordinate, the x component and the y component don't actually commute because of the commutation relations between x and pi. So now we have a space where the x and y coordinates do not commute when we project into a Landau level. An additional consequence of all of this is that the projected density operators, which are just this sum of e to the I q dot r s here is a particle index, that these density operators satisfy what's known as a Girvan-McDonald-Platzman algebra, which for those of you who know what W infinity is, this is sort of the avatar of the W infinity algebra, the lowest Landau. But this is quite exotic. All of this is very different from the physics that many of us are used to in many body condensed matter systems. Okay, so now I want to try and build composite fermions out of particles projected into a Landau level. So we're going to start with bosons. And the basic physical idea here is rather than attaching fluxes like I described a few slides ago, we're going to opt for vortex attachment. So this is something which in the wave function language leaves everything nice and in the lowest Landau level. And the major physical difference is that the vortices that I attach are going to have a charge deficit at their core, which means that now the composite fermions are neutral charge vortex dipoles shown schematically here. So if I have a vortex coordinate that I'm writing as RV, and my original guiding center coordinate for the boson R, then there's a dipole moment, which is the difference between Ri and Rv. And at nu equals 1, I'm going to attach a single vortex to each boson, such that now they have the same density, but they're going to see an opposite magnetic field. Because they're vortices, the magnetic field they feel comes from the background charge density, and so they feel a magnetic field in the opposite direction. Okay, so one cool thing about all of this is that the dipole moment itself can be shown in the next slide to be related to the momentum of this composite fermion object, which is telling us about this mixing of short and long distance physics. So if I have large dipole moment, which normally think of as very long distances, that corresponds to large momentum, which normally we think of as being in the ultraviolet. So that's where this mixing behavior between the UV and IR is coming from. Now, one naive guess, if we just have this simple picture of dipoles on the lowest Landau level, is that the Hamiltonian might just be the dipole energy. And if we make that guess, and we're sitting at nu equals 1, so again, by the same argument as several slides ago, the flux, the attachment of flux that's coming from the vortex is going to screen out the magnetic field. So then you just have this quadratic dispersion here, and so you have a metallic state, which is the right answer. So this physics of dipoles is consistent with the composite Fermi liquid language of nu equals 1. Now, what I'm going to show is that working with this really simple physical picture of single dipoles in the lowest Landau level, we can actually obtain most of our results for the Jain states without ever even touching non-commutative field theory. And we're going to explain why that's equivalent. Okay. Yeah.
Usually, vortex is vortex of something, circulation of something, right?
Right.
That in my version of physical, that is.
Yeah.
So how should I think of this vortex? You're using vortex kind of like a localized object that you can attach to something.
Right.
But vortices require some texture to be defined.
Yes. Yeah. So that's actually quite important here, is that this vortex, because it's still a vortex, is going to have some width associated with it. It's going to have a core. And that's where you get this charge deficit here. But for our purposes right now, this is really just coming from the magnetic field. So you can think about this the way that we think about flux attachment just now. Essentially, instead of taking a solenoid,
attachment is like magnetic field is distribution of field lines.
right?
And I can imagine bundling some of them and attaching. I don't know.
Yes.
Maybe I'm now kind of conditioned to take that to be natural at this point.
No, it is natural, and the IR theories are equivalent. Here, I'm doing something very similar, and really the only difference is this sort of short distance definition of
what is giving me what is circulating to give me vorticity? Should I not ask that?
I think for the purposes of right now, we should just think about this as some auxiliary object that I'm choosing to
like ether.
Like ether, sure. I think that there's probably a more sophisticated way of answering, but for all of our purposes right now, we should just think of it as an auxiliary object in the way that we were thinking about these fluxes as auxiliary objects. Rather than, because the way that we often formally define flux attachment, rather than bundling these black arrows on each charge, is to actually take some auxiliary flux, some fake flux,
Right.
and attach.
You take some gauge field and say,
Right.
There is auxiliary gauge field.
Yes.
And it was probably quite unnatural in the early days. But maybe because you have this vortex, which requires sort of a texture, and it's not a local object. Is that how you're kind of mixing IR and UV?
Yes.
Away?
Yeah, it's related to that. I mean, I think the better way to think about the mixture between the IR and UV is just the fact that there's this dipole moment. But in a way, it's coming from the texture of the vortex, because the vortex has to have its charge deficit. I don't know if that makes sense, but
right. Thank you.
And in a minute, I'll give a sort of when we talk about the non-commutative field theory, there will be an explicit place where this vortex comes from, which is like a partonic type construction. So it's similar to its origin is similar to the emergent Chern-Simons gauge field in the usual flux attachment procedure. Okay.
Can I ask one related question?
Yeah.
Can you further classify what's the difference between flux attachment and the vertex attachment? Should I simply think of vertex attachment as actual factor in the wave function, and the only difference between flux and the vertex is one is in the lowest Landau level, while the other
one's holomorphic and one is not. So one is I'm attaching a zero to a particle when I do vortex attachment. Whereas
Okay.
the wave function, the flux attachment is going to be this singular transformation that mixes Landau levels.
Okay.
Yeah.
So it's like one way to think of vertex is just the Jastrow factor.
Yeah. Yeah.
Okay.
Yeah, the level of the wave function, it's exactly that. Yeah. Okay. So now I'm going to go into a little bit more detail about how this cartoon picture works. So we have these guiding center coordinates for the bosons, which satisfy one guiding center algebra. The vortices, which see charge as flux, are going to see an opposite magnetic field and thus have their own guiding center algebra with the opposite sign. And these guys are going to commute with each other. They live in different spaces. So we can now use this RI and RV, RVI, I guess, to form a composite fermion coordinate just by taking their average. And when you do this, you get that the conjugate momentum to this thing is exactly the dipole moment up to this contraction with the epsilon symbol. So I can define this P composite fermion as just this dipole moment and see that there's a canonical commutation relation with this average coordinate and that these P's importantly commute with each other. So this is what's telling us that the composite fermions feel no magnetic field. And now we can even better motivate this Hamiltonian that I mentioned at the bottom of the previous slide as just being the square of the composite fermion momentum divided by a effective mass, which for right now is going to be a parameter. We'll be able to get it from the microscopic theory later using Hartree-Fock, but for right now, it's just going to be a parameter. Okay, so now I want to dope and get to the Jain states. So the charges are now going to have a deformed magnetic field. I take B to B plus delta B. But these vortices, which we were describing as auxiliary objects, are still going to feel the same magnetic field because the density is fixed. So now I have a new guiding center algebra for the particles, and the vortices are going to satisfy the same one. Now, we're going to define the composite fermion momentum in exactly the same way. But now, because of this difference, the composite fermion momentum does not commute with itself. In other words, the composite fermions feel their own magnetic field. But something that's a little funny is the form that the right-hand side of this commutator takes. So it's going to be this funny combination of delta B and B, which I'm going to define as delta Fxy. And we'll see it's the field strength of a non-commutative gauge field later. So just using this algebraic structure, we can just solve the usual Landau level problem in this magnetic field, delta Fxy, by introducing creation and annihilation operators built out of PCF. And spectrum is literally just a harmonic oscillator, and you get a gap, which is this delta Fxy over M star.
So sorry, can I ask one question
Yeah.
related?
Yeah.
Is the vertex operator microscopic defined?
Sorry?
Is this vertex operator RV microscopically defined? So for example, if you choose some gauge, do they have expressions in terms of the operator differential operators? Do they have a microscopic expression?
I believe, if I understand your question correctly, it'll be answered in the next part of the talk.
Oh, okay.
Yeah.
Okay.
For right now, I'm just thinking about these as single particle operators that I'm defining into existence. But when I start talking about how to get all of this from the microscopic Hamiltonian, these RVs are going to have an explicit definition in terms of an emergent gauge field.
Okay. Thank you.
Yeah. Okay. Now, this is good. We've solved the Hamiltonian, but now we have this funny delta fxy that we don't know how to interpret. So, and how do we even connect this with the Jain sequence, which is what we think that we're getting? Now, the physical magnetic field felt by the charges, we'd said at the beginning of the last slide, was this B plus delta B. And we had this fixed charge density that was just B. So we might guess that the degeneracy of the Landau levels is still set by delta B, which would mean that the filling fraction, if I set the composite fermion filling to be an integer, the filling fraction of the bosons is going to be exactly the Jain sequence. I fill P Landau levels. So this at least gives you the right answer, even though this field delta B is not the same as this delta fxy. And indeed, actually, this will turn out to be the right answer. So just from this single particle picture, now we have an expression for the gaps and a definition of the Jain sequence with the right filling fractions. So in terms of this P index here, which is the composite fermion Landau level index, we have an expression for delta in terms of the density, the effective mass, which I haven't computed yet, and the composite fermion Landau index. So this will turn out to be the correct answer for non-commutative field theory. And we can also do Hartree-Fock to estimate M star and get it from microscopics. We do this in the composite Fermi liquid state, or I shouldn't say we, Sentel and Jihuan did this in the composite Fermi liquid state. And actually we'll get results that are consistent with numerics, although in principle M star can depend on delta B. And I should emphasize that there's this correction in the denominator here of +1. This is different from what you would expect from ordinary Halpern-Lee type composite fermions, which would give you just delta B over M star for the gap, which would just give you this 1 over P here. So what this +1 is really telling you is that the non-commutativity of the lowest Landau level has played an important role in getting this expression. Okay, now I'm going to talk about how to actually get all of this from an explicit microscopic construction. So let us connect this dipole picture to this non-commutative field theory of Sentel and Jihuan. So we're going to start with this Hamiltonian, which is a contact interaction in the lowest Landau level, where these density operators satisfy this Gervin-McDonald-Flatzman algebra. And what we're going to do is essentially a parton decomposition of this Hamiltonian. So we're going to pick a fermionic representation for this GMP algebra, where we write the physical charge density now in terms of fermionic creation and annihilation operators, C dagger and C of Q, with this funny phase factor here that all this together will give you GMP. This approach was originally due to Pasquet and Haldane and was elaborated on by Nick Reed. Oh, and I'm going to, throughout the rest of this talk, I'm going to use this parameter theta, which is defined as minus the magnetic length squared. Okay. Now, there's also another copy of the GMP algebra that I can build using these C and C dagger operators, where I use a plus sign in this phase factor rather than a minus sign. And this means that there's a redundancy of description when I do this parton decomposition. So I have to fix that somehow, and I'm going to do that by introducing a constraint, which is that this rho R density operator here is going to be fixed to not have any interesting Q dependence. So it's just fixed to be this uniform rho bar. And for reasons that will become apparent soon, I know I've been saying that a lot in this talk, we can think of this like the vortex density in the earlier slides. So this is what's describing then what's going on with the vortices.
Can I ask a question? So if I start off with bare electrons, aren't these C and C like, okay, maybe you call it parton, but this formula really is just a bare electron projected down to the lowest level.
Yeah. Yeah. I mean, you shouldn't think
Except that
quite
this
of these
expression
C's and
would-
C daggers as being electrons because they, due to this redundancy, they actually are going to, they have a transformation law under physical electromagnetism, but they also transform under an emergent gauge symmetry, which I'm going to talk about in a second, where this rho r is the charge density. So they're not quite still the physical electrons.
So say if I only look at L left, that
Yeah.
would frame as just projecting the bare
Yeah, yeah. If you just look at row left, this is just the physical.
right, and it's the
electron.
usual story. You can say your C is from the bare electron, but you just strip out the charge piece and call that spin-on, whatever, fermionic spin-on.
Yeah.
It's the same thing.
Yeah. Yes. Yeah. Yeah. Exactly.
The rho r part wouldn't naturally arise out of any projection.
Right.
I guess that's the new thing that you introduced here.
Right. Right. Yep. Okay. Now we can plug this decomposition into the original Hamiltonian. It gives us a 4 fermion Hamiltonian that you can do Hartree-Fock on, assuming a metallic ground state at nu equals 1. And that will give you a composite Fermi liquid description with a particular value of the effective mass, which is related to the interaction strength. And this calculation was not done by me, it was done by Sentinel and Jihuan. Okay. Now, when we work with this Hartree-Fock approximation, that's giving us some low energy description, but we want to ask now about fluctuations about that low energy description. So the Hartree-Fock order parameter doesn't actually commute with this row right for Q not equal to 0. And as a result, this Higgs's fluctuations down of that, this will Higgs gauge fluctuation. So I haven't been totally clear about the emergent gauge symmetry in this problem, but this redundancy corresponds to a U of n transformation on the C's, and that gets Higgs down to U1. The result is a non-commutative composite fermion field theory, which I'm writing here. So this X is a non-commutative coordinate. And as a result, all products of fields defined on this space are going to be these things called Moyal star products, which for all intents and purposes, you should just think of them as convolutions. But in position space, they look like this. So it's essentially just taking these products using these phase factors that I defined. Now, with this description, the constraint that I mentioned before is implemented by the equation of motion for this fluctuating gauge field little a mu. And that's going to set this C dagger C, star C, equal to rho bar, which is the constraint from before. And the C dagger star C in Fourier space is the same as this row right on your earlier slide. I'll note also that row left you can similarly define using this Moyal product in this way. Now, you can take a commutative limit of this theory using something called the Seiberg-Witten map, which I'm not going to have time to discuss at length. But this theory turns out to, at long wavelengths, be equivalent to HLR theory with the addition of some higher derivative irrelevant operators. Now, starting with this description, then we're going to try to access the Jain states by turning on a background magnetic field, which is delta A mu. One thing I should emphasize before I go on too is that this theory doesn't have any Chern-Simons terms as written. That only actually ends up appearing with the Seiberg-Witten map as a consequence of the constraint. So written in non-commutative field theory language, there's no Chern-Simons at all. Okay. So Now, before I can derive the Jain states, I have to say a bunch of things about non-commutative gauge symmetry. So even a U1 gauge group, because of non-commutativity, actually supports non-Abelian representations. So everything, for all intents and purposes, you can think of as behaving sort of like QCD. And in particular, this means that I can define fundamental and anti-fundamental representations of U1. So there's a U1 electromagnetic symmetry, which acts to the left on these Cs, and that's the physical electromagnetism. And A then transforms, big A transforms like non-Abelian gauge field would transform in ordinary space. And similarly, you can define a right gauge action this way by multiplying the C's on the right, and little a transforms under this. And the charge densities associated with both of these things are rho L and rho R, thus the subscripts. Okay, so pushing this analogy with non-Abelian gauge theory, the gauge covariant field strength I can write in this form. So you have this extra commutator term that's new. Similarly, little f has the same commutator term, but with a different sign. And both of these things transform as adjoints under gauge transformations, again, similar to QCD. But something that's really, really weird about all of this is that unlike in ordinary gauge theories, these field strengths don't respect monopole quantization. These field strengths don't respect monopole quantization. The gauge theories do. Instead, the thing that satisfies flux quantization is this funny combination I've written here. I'm not going to derive this, but you can see in the appendix of our paper justification for this. And this is really, really weird. I've never seen any theory like this where you have this kind of singular object that is determining quantization of flux. I think the only examples appear in this weird non-commutative context. Now, finally, final facts that I'm going to say about non-commutative gauge
I
symmetry.
have a question here.
Yeah.
So what's this capital theta here?
Oh, this capital theta is minus the magnetic length squared.
Okay.
Yeah, I defined it a couple slides ago. Sorry. Yeah, I halfway through the talk switched from using LB explicitly to using theta, but it's the magnetic length squared with a sign flip.
So I think if you plug B back in, then this just means B times area equals integer.
Yeah, exactly. So if you're getting ahead of me, but if you plug in up here, then what you'll find is that this is the delta B that we met in the single particle problem. Okay. Now, the last weird thing I'm going to say about non-Abelian gauge invariance is that it's actually related to coordinate transformations of space. So a area preserving diffeomorphism, which is just this local coordinate transformation that preserves area, can be written as an adjoint gauge transformation in this way. So you satisfy this relation here. And what this means is that you can now construct new, what we call covariant coordinates, which I'm calling capital Y and capital X here, where now gauge transformations on big A and little a induce adjoint gauge transformations on big Y and big X because of this relation here. And so we can rewrite the covariant derivative of any operator as just the difference between star product with Y and the star product with X on the right. So this, one other sort of side fact. If anyone's familiar with Chern-Simons matrix models, these are the basic variables in the Chern-Simons matrix model. It's the same. Okay. Now that I have all of this information that's built up about non-commutative gauge theory, I'm going to define suggestively new operators, R and RV, acting on C. And this is, to answer the earlier question from, I think, G, this is where RV comes from in the microscopic theory. And you define the operators in this way via star product on the left with Y in the case of R, and star product on the right with X in the case of RV. And now the composite fermion Hamiltonian can just be written as a dipole energy exactly. It's just the difference between R and RV here squared.
What is the last C then?
Sorry, this is H acting on C. So that's where the C is coming from. Yeah. I should delete that because you're not the first person who's asked me that question when I've given this talk. Okay. Now we want to study then the mean field theory of this problem with a uniform background delta fxy, which is this non-commutative field strength for big A, and with vanishing field strength for the little a. So these R operators then satisfy the following algebra, where the RVs just are, they don't commute to plus LB squared, but the Rs, they don't commute to some funny combination with delta F, which I'm going to now define as a new magnetic length associated with B shifted by a new field, which I'll call delta B hat, which is written in this way here. But delta B hat, first of all, it's the field that gives you the correct flux quantum, as I mentioned in the previous slide. And therefore, it's really what we should be interpreting as the physical magnetic field. That's what's giving you the degeneracy of the non-commutative Landau levels. So what this then means is that because these algebraic structures are the same, the mean field Hamiltonian and the dipole quantum mechanics model are exactly the same. And they give you composite fermion Landau levels with degeneracy that's set by delta B hat. And indeed, you get a gap, which is exactly the gap that we met with the dipole quantum mechanics problem. So really, if you get anything out of this talk, it should be the simple single particle picture. And whenever you think about non-commutative field theory, probably the best way to think about it is in this, just physics of dipoles. And if you understand the more technical field theory representation in terms of these composite fermions, great, but all that physics is the same. Okay, so in my very last part, I'm going to talk about where non-commutative Chern-Simons theory comes from. So we can integrate out the composite fermions, just like in ordinary HLR theory, or I should say Lopez and Fradkin. But I don't think Eduardo's in the audience, so I'm not going to get corrected by that. To obtain both the topological order and the Hall conductivity. And by directly evaluating the composite fermion functional determinant, we can do this calculation, but it's actually a lot cleaner to do something much simpler, which is to just compute the drift velocity of the charges in this charge vortex quantum mechanics picture. So we, again, I think I mentioned in an earlier slide that functions of y and x, these covariant coordinates, transform as adjoints under left and right gauge transformations. So we're going to introduce scalar potentials, which also transform as adjoints. I'm calling VB of R. This is like you can think of this as a scalar potential for the bosons, and VV of RV, which is scalar potential for the vortices you can think of. And the corresponding electric fields we define using commutators with the R's, because in non-commutative space, these are derivatives. So we define them this way. And we'll also define currents as just being time derivative of R and RV. So we'll work in the Heisenberg picture where R and RV evolve in time. Now we can write down the Heisenberg equations of motion just using the commutators with the Hamiltonian, and we get this family of equations for PCF, R, and RV. And in order to solve these equations, we have to actually introduce the constraint from earlier. In other words, what happens when you integrate over the fluctuating gauge field. So that gives you this fixed density, but it also gives you that the composite fermion momentum vanishes. Essentially like saying that the composite fermions and the vortices are sitting on each other, because remember, this is the dipole moment. And this then immediately means, on inspecting the equation for RV, that the vortices have Hall conductivity -1, just like we've been saying much earlier, that they live in this nu equals -1 filling. So this is consistent with that. And the constraint, then further plugging into the other two equations, gives you a relationship between big E and little e in terms of the ratio of these respective magnetic lengths, which in a Jain state is related to the composite fermion filling in this way. And the correct physical Hall conductivity then can just be pulled out as being P over P plus 1, exactly what we want for a Jain state. So we can plug all this back in and sort of try to reconstruct what the Chern-Simons Lagrangian would be, given all of this information here and here. And so you just get this effective expression up to order theta. But these gauge fields were non-commutative, as I was saying. So at least for the case of A prime equals 0, don't ask me about A prime non-zero. It's a much more complicated story. There's only one possible gauge invariant action that's local in these Moyal star products, and it's just the non-commutative Chern-Simons action. And this is what we also get from just evaluating the functional determinant. So this is the same theory that was proposed by Lenny Susskind and Polychronikos 20 years ago as a description of the fractional Hall effect in the lowest Landau level. But the physical relevance of that whole story was really unclear until we came along. And the topological order of all of this is related to, for the experts in the audience, spin C U1 to the level P plus 1 Abelian Chern-Simons theory. And yeah, I already said this. Okay, so just to close, our lowest Landau level theory is able to capture both microscopic and topological features of at least the bosonic Jain states, which is really not something that anyone has ever done before for the study of the fractional Hall effect. And there are all kinds of interesting future directions. So first, we haven't really been able to access yet things like the static structure factor or the Hall viscosity, physics of the magnetoroton mode using this picture, but it should all be there in this framework. It's just a matter of computing. And we also should probably improve the estimate for the effective mass. So we used the value from the composite Fermi liquid state that was computed by Senthil and Jihuang, but that's only a good approximation probably for large but not too large composite fermion filling. So if you get very close to the nu equals 1 composite Fermi liquid state, then gauge fluctuations of little a are going to become important and spoil the estimate that you get. And similarly, if you go very far away, you might think you're safe, but then because you're so far away from the composite Fermi liquid state, then in principle, you can have a large magnetic field dependence of the effective mass. So you want to be in a sweet spot, essentially, between small and large composite fermion filling for our approximation to make sense. Although we get an answer that's fairly consistent with numerics. I think it differs by a factor of 2. So the other big thing that I mentioned in passing last slide is that we don't know how to write down a gauge invariant mutual Chern-Simons term for these non-commutative gauge fields. I should mention there's some recent paper by Damson and his students that sort of made progress in this direction by relating everything to gauge fields for these area preserving diffeomorphisms and things. But really, we still don't have an answer for a mutual Chern-Simons term between 2 non-commutative gauge fields. So really, if progress on that has made, then all kinds of things are more easy to understand. And of course, the biggest problem looming over all of this discussion is how can we write down a lowest Landau level theory for fermions at nu equals 1/2. So in this talk, we were able to leverage this picture of charged vortex dipoles, and that gave us composite fermions because we were working with our original charges being bosons. But now when we're working with fermions at nu equals 1/2, we have to work with 2 vortices instead of 1, and things become much more complicated much more quickly. So hopefully we'll be able to make progress on this soon, but that's the major overarching problem here. And with that, thank you, and hopefully if there are any questions, I'm happy to discuss.
Questions? Go ahead.
I have a question. Can you say more about the recent paper by Song? So they also start from this area preserving the homomorphism, and how's their construction different from the Seiberg-Witten map?
From the Seiberg-Witten map?
Yeah.
Yeah, so basically what they end up having to do is they write down this theory which has gauge fields which transform under full area preserving diffeomorphisms. And they develop a Seiberg-Witten map of that theory to a ordinary V1 theory. And then their claim is that, well, they can then do a reverse map from the commutative theory to some non-commutative theory. But there isn't a direct map between the APD gauge theory and the non-commutative gauge theory. It's kind of, to quote my advisor, it's scratching your left ear with your right arm a little bit.
I have a question, and it's possible you mentioned this, but so for the HLR theory, if you include the effects of the gauge field fluctuations at the RPA level, you get a marginal Fermi liquid.
Right.
Is that the same here if you include the gauge field fluctuations, or is this different?
So when I'm sitting in the compressible state,
yeah,
it's fairly difficult to calculate dynamical quantities within the non-commutative field theory. So the recourse for doing that is to use this thing called Seiberg-Witten map. And that's just going to give you literally HLR plus some quote unquote irrelevant operators that become active at the scale of the magnetic length. So the argument that you get a marginal Fermi liquid out of HLR can be applied directly to that theory. But I don't know how to for example, construct a Nyack-Wilczek type fixed point for this non-commutative composite Fermi liquid theory in the compressible state. I think that there's an easier chance of being able to compute all of this stuff for the gapped phases, but yeah, sitting in the compressible state, I don't know. It's an interesting question and it's worth exploring more. Not like very few people have studied non-commutative field theory at finite density and field. So it's a very, despite the vast literature on non-commutative field theory, there's, we're kind of the pioneers in that area.
All right. Other questions?
So it looks like I might have missed parts, but you're comparing mean field theory of the non-commutative field theory with your single particle description.
Yeah.
Is that right?
Yes.
So essentially you're saying if you're going to stop at mean field theory, you don't have to do all that complicated stuff. Just swallow my single particle physics.
Right.
Perhaps the virtue of having a full-blown field theory would be to, I don't know, handle some fluctuations.
Right.
But I don't know what people did with the non-commutative field theory, which is a complicated object beyond mean field theory. Have people done things beyond mean field theory?
For this type of problem, I don't think so. So I think that
So maybe I don't have to learn anything about non-commutative field theory, because they've only done mean field theory, and you've got a simpler version of, mean field theory.
Yeah.
It looks like you're doing something with wave functions secretly, right?
Yeah, that's exactly what's going on under the hood. And that was sort of the big surprise when we were writing all of this up and sort of the story was coalescing, was just how much could really, about the mean field problem, could really just be understood in this single particle language. As far as handling fluctuations, there are a couple of ways to answer this. One is that, I think that there's still a fair amount that can be done that hasn't been done in trying to capture fluctuations in these non-commutative theories, just taken as such. But there's this additional thing called the Seiberg-Witten map, which I think it was Dan who mentioned, where this theory then gets mapped to HLR plus ... And so you can work with fluctuations in that theory, modulo all of the problems with understanding fluctuations in non-Fermi liquids, and try to include the effects of these irrelevant operators in calculating UV sensitive quantities. And hopefully that matches the non-commutative field theory. Although there's an asterisk to all of this, which is that that equivalence is classical and not quantum. So there's no guarantee that quantum correlation functions match between the two descriptions. So that's a caveat.
Have you explicitly written down the many-body wave function? I mean, I guess not many-body. And anyways,
for
function,
the
some sort of product state or
for
something.
the compressible state.
Yeah. Have you written down a wave function? No.
For the compressible state, no, except for you can do mean field again, but I think that you want something perhaps more exact.
Yeah, I mean, your vortex attachment, it sounds like you can literally write a wave function that articulates that. And perhaps
for the gapped phases, yeah. For the
Yeah.
gapped phases, yeah.
And with a wave function, you can do sort of concrete things.
Yeah.
Calculations.
Yeah, and this also connects with these matrix models that I mentioned as well. So when you get this this Chern-Simons theory at the end, you can write a mapping of this theory to a essentially quantum mechanics model where the world line coordinates are matrices. And you can show explicitly that the ground states of those theories are, at least in some long distance approximation, Laughlin wave functions. So this was what led Polychronikos in particular to want to sell this as some major microscopic theory for quantum Hall states. But yeah, within the Chern-Simons theory, even itself, you can get some wave function description using essentially the coordinates that we've been working with.
I have a couple of related questions.
Yeah.
So when you derive the dipole models, you simplify the composite Fermi liquid Hamiltonian to a very simple form like dipole squared.
Mm-hmm.
Where is the interaction term?
Good. So from the point of view of the single particle problem, that's just a guess. Okay, I'm not thinking about interactions. The hope is that the interactions get hidden in the effective mass. Where is it? Here. So now within the sort of Pascal-Haldane field theory type approach, where I start with the real Hamiltonian and this GMP algebra, and I do this decomposition, then when you do Hartree-Fock on this, you do get the dipole energy, where the effective mass is being determined by this U naught. So indeed, it's being hidden in the M star. But as it stands in this sort of cartoon single particle picture, I'm kind of hiding the interactions and not working with them in a serious way. So you do need the full technology of this Pascal-Haldane type approach in order to actually calculate certain parameters in the theory like M star.
Mm-hmm. Okay. So my second question is kind of more general.
Mm-hmm.
So if we want to keep all the non-commutativity information from them, we can do numerics. We can just diagonalize this non-commutative problems directly in the lowest lemma level.
Mm-hmm.
So in your opinion, what is the most interesting thing that non-commutative field theory can bring in that numerics cannot do?
The numerics cannot do.
Yeah.
So I mean, as you already said, numerics is the, it's a set of techniques which historically we've been able to use to really access all kinds of quantities like gaps and things. I think the advantage to having a field theory, if you can calculate things with it, is like compared to numerics, is that you're not limited to finite size systems. So most of the numerics is, as you know very well, is ED, and still is sort of limited to relatively small system sizes. But if you have a field theory where you can, in principle, calculate anything you want in some uncontrolled or controlled approximation, that can give you a complementary, intrinsically many body answer for different things.
Yeah.
And as far as the other thing is a statement about symmetries. So the field theory should give us a clear understanding, for example, of how Son's theory would appear at nu equals a half as a low energy effective description, and where particle hole symmetry comes from. Or in, it would tell us if in the quarter filled state, for example, if this reflection symmetry that I've written about, and you've also written about these types of theories, if that is a lowest Landau level property, or if we have to think about that as some emergent symmetry that comes from disorder or something. So that's a very concrete physical question that can be answered by having a sort of lowest Landau level field theory for nu equals a fourth. Of course, we don't even have nu equals a half yet, and that's a fairly challenging problem. But hypothetically, if we had these things, there's quite a lot we could learn.
So you're saying the first is the finite size
G,
limit,
G.
not. Hi.
Yes.
Yeah.
Those of us who are here in the room have to have cookies. Yeah.
Okay.
So we have to move
Oh,
on to
I'm
cookies.
really envious.
Maybe.
But before that, let's thank Hart one more time. So
Hopefully you guys can continue discussion